Greetings again from Rescue Shuttle Control. Given the great progress that you've made over our last few sessions in developing and understanding our security systems and logic, we're in a good position now to move forward with some more understanding that will allow us to control systems on the shuttle. And today, our focus in terms of control will be on examining a new hardware item and the software necessary to use that hardware item. We're going to be understanding how to control and input information using a rotary encoder. A rotary encoder is a device that allows us to turn a shaft or a knob and have that correspond to numerical or data information that can be accessed and used by our hero system. You have in front of you on the screen right now an example of a rotary encoder. And there are different types of rotary encoders. Some are so-called absolute encoders that give a unique correspondence between an angular position of the knob and the value that comes out. So such an absolute encoder would have a maximum clockwise and a maximum counterclockwise position. On the other hand, there are relative encoders that you can turn around any number of times. And instead of giving you an absolute angular position, it tells you relatively how much the knob has been turned clockwise or counterclockwise since some original position. The latter is what we'll be using here today. We have a relative rotary encoder, and as you can see right here, it has a number of pins on it, which we'll discuss shortly. The shaft of the encoder I can rotate, and as you experiment with your encoder, you'll find that it has a number of click positions that it rotates to. If you carefully count, this particular encoder has 20 positions that it clicks through as it goes through a full rotation of 360 degrees. So each one of those little click positions corresponds to 1/20th of a circle, or in other words, 18 degrees. So this would be a rotary encoder with an angular resolution of 18 degrees. Now, what we want to learn is how those rotations translate into outputs that come out of the pins of the encoder. So let's talk next a little bit about what those pins are. You'll notice that this encoder has 4 pins. The last 2 pins, the lower 2, are labeled plus and ground. And those should be familiar to us because those would be the familiar power supply and ground values that we've encountered in using some of our other devices. So we'll hook up a constant 5 volts to plus and 0 or ground to the ground pin, and that will power our device. The other 3 pins are the ones that we'll be paying a little bit more attention to, and really we'll only be paying attention to 2 of them. In addition to this particular encoder being able to take rotary information, it turns out that it also has a switch in it which can be activated by pressing down on the center shaft. While that's a feature of this encoder, we won't be using it today. And so as a result, we're going to ignore the switch function, although we may have occasion to use that later on. That means that the center pin, labeled SW for switch, is one that we will not be using today. Instead, we'll be paying attention to the top 2 pins labeled CLK, or clock, and DT. Now, those names aren't particularly helpful for us today because they're really just of historical significance as far as we're concerned. We might as well just refer to them as A and B. And so I'll talk about those two pins, A and B, that way for the next few minutes, although we will use the CLK and DT to distinguish them when we're writing our code. All right, what does a rotary encoder of this kind do for us? As we turn the shaft, we'll find that an output, a digital output, is produced that's described more or less by this sketched graph right here. As we rotate either in the clockwise or in the counterclockwise direction, as we go through each of the click positions of the encoder, we'll see the output transition, say, from low to high, from 0 to 5 volts, or from high to low. And those transitions will tell us each time we've moved through another position in the rotary encoder. Now, you might think that all we need to do is have one output of that kind, because if we count the number of transitions that go by, we can use that to infer how many rotations or how many fractions of a rotation have been performed. And that's true as long as we don't care about which direction we're rotating. But we would like to be able to track whether the rotation was clockwise or counterclockwise. And that's why we need not one but two outputs from our encoder. And that's the reason why we have A and B, or clock and DT. How does that help? Well, the way it works is this. The two outputs, A and B, do not transition exactly at the same position of the knob, but they're staggered with one another. So you'll see that, for example, as we rotate clockwise, for example, and we look at the output of A will transition from low to high first, and then a little bit later, B will transition from low to high. And so this tells us that if we see A go high first and then B, then we're rotating clockwise. And on the other hand, if we see B go high and then followed by A, then that tells us we're going the other direction. We're rotating the shaft counterclockwise. So you can see how this is going to help us in being able to determine the state of rotation of the encoder. One more thing that we'll basically be using when we look at the code that reads these outputs is we want to be able to keep track of how many transitions we've made, either in the clockwise or the counterclockwise position, and keep a tally running so that we know the position of the encoder relative to its starting position. And in any given transition, let's keep our attention, say, on just transitions from low to high, from 0 to 1. So let's have a look at A and see that when A goes from low to high, immediately after that transition occurs, you'll find that the A pin is high, but the B pin is still low. So those two are different from one another. So we will use that as an indicator when we see A go from low to high and A is different from B, then we know that we've been rotating clockwise. On the other hand, if we were to see A go from low to high, and immediately after we saw A and B were the same, then we would know that we were rotating counterclockwise in the opposite direction. So we'll use that exact type of reasoning when we construct our code that interprets the output of this encoder. All right, with that little introduction out of the way, I think we're ready to go ahead and examine both our hardware and our software necessary to make use of this new capability. As you'll see now in front of you, we have the Hero connected to a rotary encoder, just like the one that we were just examining. And I'll point out a little bit about the features of this setup just so that you can understand. You'll see that the ribbon cable has got the blue wire connected to ground and the green wire connected to plus 5 volts, connected over here to the 5-volt pin on the Hero. As we discussed before, the switch pin is unused in this example, and we'll just use A and B, clock and DT, corresponding to the red and the orange wires of the ribbon cable. And if you look carefully over here where red and orange go, red is connected to pin 2 and orange is connected to pin 3. All right. Now, that's essentially all we need to understand in order to figure out how the Hero is communicating with the encoder. There's one additional thing to point out, which is really just going to be review for us today, and that is we've decided to hook up our 7-segment display to some additional pins on the Hero board so that we can take the results of our manipulating the rotary encoder and display them as numbers on our digital display. And so for that purpose, we've gone ahead and connected up the 4-digit display, the 7-segment 4-digit display, to some of the unused pins on the Hero board. And we'll talk about those a little bit later, but they're a little bit tangential to the main point of today's discussion. All right, with that out of the way, let's go ahead and direct our attention now to the code that we need to introduce in order to understand how this encoder is going to work. We'll be introducing a new concept today that we haven't used before, and this is the concept of an interrupt. An interrupt is a device in our software that allows us to take an unexpected or an unanticipated event and have the software respond to that event rather than having something that's programmed ahead of time. All right, let's have a look now at our code. Since we are going to be using the 4-digit display, we've included the display library here as we'll be needing it. But our main concern right now is to see what's happening with the rotary encoder. We've defined a couple of new equivalences here. We've defined clock 2 and DT2 to correspond to the pins 2 and 3 on the Hero, as we just discussed. We will talk later about the display, but we've decided to set the CLK and DIO pins for the display not to be confused with the pins for the encoder to 5 and 6. And looking over at the Hero, I can see that 5 and 6 do in fact correspond to the purple and brown wires that are connected to the 4-digit display. All right, but let's keep discussing, rather than talking about the display that we've learned about before, let's keep talking about some of the new material that we have just learned about in today's session. So I'm going to scroll through the material here that covers the display and get to some of the new material. We have an integer variable here named counter, and its name says what it does. It's going to keep count of how many encoder clicks we've gone through. Every time we go clockwise, we'll increment counter by +1. Every time we go counterclockwise, we'll decrement it or decrease it by 1. And that will allow us to keep a running tally of where the position of the encoder is. Now, we also want to keep track of just what the current state is, either high or low, of the pins of the encoder. And so here's another variable, current state CLK, current state clock. Remember, that's our pin A on the encoder. And another variable that allows us to remember what it used to be, last state CLK. So current state and last state are going to allow us to determine whether or not there's been any changes that have occurred. We're also going to be writing some things to the display, and so we have a string variable here, which is just an array of characters, and we'll fill that up with things later on. All right, now we're going to be getting to something rather important here in the setup routine, and so let's talk a little bit about that. First off, we do have to take our CLK2 and DT2, those are the two pins on the encoder, and set those to inputs on the hero. So that means that the hero is going to be expecting digital input from those pins on the encoder. We're going to be sending some information out, and we want to send it out over the serial monitor as well as the display. So we're going to begin the serial monitor as we've done in the past. Now, we're going to begin with this setup routine by using the digital read on the A pin of the encoder to see what the baseline state is. So last state CLK will be set to whatever value we get when we read CLK2. Now, we're going to clear the display so that it's ready to go. And now we get to the really important new concept. Once at the beginning, during setup, we're going to call a routine called attach interrupt. Now, what attach interrupt does is it takes the pin A, which we've named clock 2, and pin B, which is we've named DT2, and it takes the digital pin on the hero corresponding to those, and it checks to see whether the encoder has changed its status. If any change is detected, the fact that we have called attach interrupt in the setup means that any time later during loop, for example, any time that one of these pins changes, there will be an interrupt declared. And what happens is when an interrupt is declared, a special routine is called. This routine is called an interrupt service routine, or an ISR. And we have to supply it. We have to tell the hero what to do when an interrupt occurs. And we're going to see exactly what that interrupt service routine is in just a moment. But the name of our interrupt service routine is update encoder. That's the name that we've given it. So keep that name in mind, because that will be the name of a routine that we'll see in just a moment. So once we've attached interrupts for our two pins on the encoder and connected those with the ISR, we're done. That's all that happens during the setup routine. Now, normally at this point, we would go ahead and start to dissect the loop routine. The loop routine doesn't really have anything too interesting, although we'll come back later on and look at it quickly to see what it's doing. So we're going to skip over the loop routine right now and go directly to the interrupt service routine, the ISR, because that's where the new learning is happening here today. So let's scroll down past loop and get to the ISR. You'll see from the comment here that this is the ISR that has the job of responding to interrupt events. So anytime a change in status from low to high or high to low is detected, we'll jump into this routine called update encoder. So what have we written inside update encoder? The first thing we do is we check the current state of CLK, current state of pin A, using digital read, just as we did actually before in setup. In setup, we saved that value in last state CLK. Now we read it and put it in current state CLK. All right, now some logic happens. We want to only react, we only want to do something if the current and the last state of CLK are different. Now, presumably they are different because we wouldn't have gotten to this point unless an interrupt had been declared. But we want to respond if the change is from 0 to 1 and not from 1 to 0, because we don't want to count twice every time we go through one of the click positions. We only want to count once. So you can see that the test here says if current state is not equal to last state, and if current state is right now equal to 1 or high, then that means, okay, this is one we want to count. So what happens next? If the B pin is different than the A pin, you'll remember that that means that we are rotating clockwise. So here we're going to do a digital read on the B pin on DT2 and say if that is different from current state CLK, then we were rotating clockwise. So there's two things to do. Set current direction, that, remember, that was our string variable, to be CW. So CW is just shorthand for clockwise. And take the counter variable and add 1 to it. So if it started at 0, it will now be 1. If it was at 1, it will now be 2. All right, what if this is false? What if digital read is the same? What if the status of B is the same as A? Well, that is handled by else down here. That means the encoder is now rotating the opposite direction. It's rotating counterclockwise. So that means that we need to set the current direction string to CCW, counterclockwise, and we need to decrease counter by 1. So if it was at 0, it will now be -1. If it was at 3, it will now be 2. So we've now taken the appropriate action depending upon whether the rotation was clockwise or counterclockwise. We're going to print some information out to the serial monitor. And so here we're going to print out the current direction and the current value of the counter, and we'll see how that comes out when we test our code. And finally, the last thing we do before returning from this interrupt service is to save the current state as last state. So we're going to replace last state with current state so that we'll now be able to compare the next time an interrupt occurs and see whether or not a change has happened. All right, so that pretty much covers everything that needs to happen in our ISR. And so the last thing to do before we test our code and run it through its paces is to go back and see what's happening in loop. And as I promised, what's happening in loop isn't too new to us. It's really just a way of taking the information that we get from the encoder and use it to do something on our display so that we can sort of get a little bit of feedback as to what's happening. And so you can see that you can customize this code however you like, but we've chosen to just do some very simple things here. Well, we start off by taking our display and showing the current value of counter. It should start off at 0, but as we rotate the encoder, we should see it either increase or decrease in value. Next, after a short delay, we do a test. If counter has reached 50, then what we're going to do is tell our display to sort of flash all bars on for 2 seconds and then clear. And then we'll just continue with loop. Next time we come through loop again, it'll show us the counter again, but it'll be frozen with all bars on for 2 seconds just to let us know that we reached 50. There'll be another pause to display when we reach 75. And then finally, just as a very simple example, when the counter reaches 100, we'll again pause the display, but this time instead of displaying all bars on, we'll display the alphanumeric code done and keep that on for 3 seconds before then clearing and returning back again. So it's a very simple function, just intended to let us know if we are really taking the information and using it successfully. All right. Aside from explaining what all these various arrays do, which we've explained in previous sessions, I think we're done. So the next thing for us to do is to validate our code, compile it, make sure it doesn't have any syntax errors in it, upload it, and test it and see whether this is going to do what we want it to do. What I'll do is I'll compile and upload the code, and then we'll bring up the serial monitor so that we can watch the serial monitor at the same time as we watch the display and see whether things are working as intended. All right. First, let's verify our code. All right. The compilation was successful, so it looks like we don't have any obvious errors in the code at this point. Let's go ahead and upload our code. So as we upload the code, we'll be going through the setup routine, which means that we should be initializing interrupts. And as you can see now, our counter is initialized to 0, which is what we were hoping for because we haven't rotated the encoder yet. So as I rotate the encoder now, we should be able to see changes both on the serial monitor and on the display. So I'm going to rotate the shaft clockwise a little bit and see what happens. So there's one rotation to the right, and we see that the display went from 0 to 1. And on the serial monitor, it says we rotated counterclockwise and the current counter position is 1. So that's good. I could continue rotating clockwise. So if I continue rotating clockwise, and I'll just notice something here. We may encounter some unexpected results occasionally, particularly if we pause or rotate backwards or rotate really fast. It's possible that we may skip a count, and you'll notice that we got an unintended backwards count to 0 at one point there. So this will be an issue for us when it comes to writing high reliability code. We may need to be aware of that. For the purposes of today's example, however, we're not going to worry too much about those counting errors. So let's keep testing. As you can see, as I continue to rotate clockwise, I can get higher and higher counter values. I can go backwards and count down. So let's count down. You'll notice now as I'm counting backwards, the serial monitor is indicating I'm rotating counterclockwise, and the display is counting down. I can go all the way down to 0. And I can go backwards, so I can go to negative values. So there's -2, -3, and so on. So I'm apparently getting the correct behavior here from my encoder and the hero. So one more thing for us to test, and let's see whether or not our logic that controls the appearance of the display based on what happens with the encoder works as well. So you remember that we have a special threshold that happens when our counter reaches +50, +75, and 100. So we can go ahead and rotate forward rapidly. So I'm going to spin it forward into the positive numbers. We're up to +22, 23, here we go. Okay, we're getting close to 50 now, so there's 45, 47, and now we've gone past 50. We actually went to 51. And you notice that for 2 seconds, the display went all bright and then returned back to counting mode again. So now you can see I can continue counting forward up towards 75. There's 73. Now if I go up to 75, actually overshot it a little bit, went up to 77. And so finally, our last test will be at 100. So we'll turn this up to 100, 95, clockwise, and there we go. So we've reached 100, and if I go past 100 by 1, there's 101, and I can continue using this. If I go backwards and encounter 100 again, you'll see that I trigger the done display again, and I can continue to rotate this down past 75, past 50, and on back down to 0 and negative numbers as well. So it looks as though, aside from the occasional counting errors that we get here with this encoder and this interrupt system, that this is displaying all the behavior that we want it to. So this should be a new capability that we can use for controlling systems. And I invite you to go ahead and work on this on your own, perhaps customize this to do things that occur to you that might be useful or instructive, and enjoy this new capability. And with that, we'll sign off until our next session. And remember, build everything and invent safe.